Hey, welcome. Today we're going to dive into one of the most brilliant, mind-bending ideas in all of physics, statistical mechanics. It's really a story about how scientists, staring down an absolutely impossible puzzle, managed to find perfect, predictable order hiding inside complete and utter chaos. So, let's get into it.
All right, so first, let's just appreciate the sheer scale of the problem that physicists were wrestling with back in the 19th century. I mean, they were facing a question so massive, it seemed like you couldn't even begin to answer it directly.
I mean, seriously, just look at that number. Forget predicting anything. How do you even start to think about that many individual things? Each one has its own position, its own speed, they're all bouncing off each other. It just feels like a complete dead end.
And look, this isn't just some abstract number we pulled out of thin air. This is about how many molecules you'd find in a simple jug of air. Trying to track every single one of them, its path, its collisions, its energy, it's beyond impossible. You couldn't do it with every computer on Earth combined.
So here's the core of the problem, right? If you can't possibly know the details about any of the individuals, how on earth can you know anything about the group as a whole? This was the challenge, and solving it meant they had to completely change how they looked at the world.
And that big change was to just stop. Stop worrying about every single particle and start thinking about the system as a whole. Instead of trying to get this perfect, detailed picture, physicists turned to something else entirely, the power of probability and statistics.
Okay, let's break this down with a couple of key ideas. First up is the microstate. A microstate is like a single, perfect snapshot of the exact position and momentum of every single particle at one instant. For our coin flip example, it's knowing the specific outcome. Heads, then tails, then heads, then tails. It's the God-level view of the system that we can literally never, ever have.
But a macrostate, that is what we can see. It's the big picture stuff. The properties we can actually measure, like the overall temperature, or the pressure, or the volume. In our coin toss game, it wouldn't be the specific sequence. It would just be the final tally, 2 heads and 2 tails. It's the real-world result that all those hidden microstates create. And this is where it all clicks into place. Look at this coin toss analogy. Let's say we're flipping 4 coins. The macrostate we might observe is 2 heads, 2 tails. But check it out, there are 6 different ways, 6 totally distinct microstates that give you that exact same result. Now, compare that to getting 4 heads. There's only one way for that to happen. So the 2 and 2 outcome is just way more probable because there are so many more ways to get there.
So, armed with this new way of thinking, scientists came up with some truly powerful tools. We're talking about a few key concepts and one absolutely profound equation that would let them unlock the secrets of these massive, chaotic systems.
Okay, this right here is Ludwig Boltzmann's famous equation, and it is so much more than just a bunch of symbols. It's a bridge. S is entropy. That's a macroscopic thing we can measure, basically a measure of disorder. And W is the number of all the possible microscopic ways, or microstates, that the system can be arranged. That K is just a constant to make the math work out, and the ln is there to handle the ridiculously huge numbers. But the big idea? It connects the microscopic world of W to the macroscopic world of S.
And that's the magic trick. For the very first time, physics had a rock-solid mathematical link between the hidden, chaotic world of atoms and the stable, measurable properties we see every day. The more ways a system can be arranged, the higher its W, the more disordered it is, and the higher its entropy, S. It's why a broken egg doesn't just magically put itself back together. There are just astronomically more ways for it to be broken than to be whole. It's probability itself defining the arrow of time.
So, if Boltzmann's equation is the bridge, then the partition function, or Z, is the master key to the whole city. You can think of it like this master calculation that basically sums up and weighs all the possible energy states a system can be in. Once you figure out Z for a system, you can use it to derive almost everything else you'd want to know: average energy, entropy, pressure, you name it. It is the absolute engine room of statistical mechanics.
Okay, so we've got the concepts, we've got the tools, now it's time for the payoff. Let's see how these ideas reveal this beautiful, predictable order that literally emerges right out of all that microscopic randomness.
Take the speeds of gas particles, for example. Any single particle could be moving super fast or super slow. Its individual speed is totally random. But when you step back and look at the whole group, you get this incredibly predictable pattern, what's called the Maxwell-Boltzmann distribution. You'll find that most particles are just clustered around some average speed, and very, very few are going extremely slow or extremely fast. You get this stable, predictable pattern from a completely chaotic crowd.
So down at that microscopic level, what's really happening? Well, it's just this invisible, frantic dance. You've got countless atoms zipping around, smashing into each other, swapping kinetic energy. It's fundamentally random and completely unknowable in all its tiny detail.
But what's the result of all that microscopic mayhem? What's the macroscopic property we actually feel? It's temperature. That smooth, steady, measurable thing we call temperature is nothing more than the average kinetic energy of all those individual, frantic particles.
And this isn't just some vague concept. It's a precise mathematical relationship. That impossible problem we started with, tracking 10 to the 23rd particles, gets elegantly solved by just taking a simple average. And that is the incredible, beautiful power of statistical mechanics.
Now, you might be thinking, okay, that's a clever piece of physics, but this is so much more than a theory. This fundamental understanding of how order pops out of chaos is literally the bedrock of the modern world that we all live in.
I mean, just think about it. How do we design the incredibly powerful engines in our cars or the refrigerators in our homes? It's all based on the principles of heat and entropy. How do we understand the solid crystal structures of metals or, get this, the behavior of electrons inside the computer chips that power our entire world? It all comes back to the predictable averages that we find using statistical mechanics.
So the big thing to really let sink in is this. The reliable, predictable, engineered world that we build and depend on every single day is constructed directly on top of a foundation of absolute microscopic chaos.
And that kind of leaves you with one final thought, doesn't it? If something as fundamental as temperature is really just a statistical illusion, the most probable outcome of a chaotic game, what other properties of our world are just the most likely average of some random process happening on a scale that's way too small for us to see? What else is hiding right there in plain sight?